Okay, so going through a little bit of a review of the loop rule, we're going to review it now, and then in a little bit we'll end up using it to do some other things. But it's been a while, so we'll take a look. The loop rule is usually used with electric potential or voltage. And what we do when we're measuring electric potential or voltage is we take these probes and we always have to have some place that we consider to be zero, and the black probe is just where we tell the circuit things will be zero. So if I put the black probe there, we're saying that is 0 volts. And then if I put the red probe on that exact same spot, it says comparing the electric potential at the red probe to where the black probe is, that's the reading on this on the voltmeter. So if I'm telling it this is 0 volts, and then I ask it by putting the red probe here, what's the potential there, what's the voltage? Well, I told it that's 0, so the reading is 0 volts. Now, if I go to this other spot on the top end of the battery, does the battery end up adding electric potential or removing electric potential? Does the battery provide volts or use volts? That's right, it provides volts. So here we're at, now it adds 9 volts. So we were at 0 down here, well, compared to 0. And now up here, the potential or the voltage has increased. If this is 0, we're now at plus 9. So that's telling us the electric potential or the voltage at this point when this is what we're saying is 0. Now, does a wire use voltage? Does a wire use voltage, yes or no? No, correct. So here, the voltage or the electric potential is still 9. And the electric potential here is still 9. And our ammeters that measure current, they're just like our wires. We're considering our wires and our ammeters to be like an electric circuit equivalent of our frictionless surfaces first semester. So first semester we would say something had friction that was small enough to ignore. We're kind of saying that same thing about these wires and this ammeter. The electrical friction or the electrical resistance is small enough to ignore on all of these. So 9 volts, 9 volts, 9 volts, 9 volts. So we said 0 volts, 9 volts, still at 9 volts. Nothing has used energy. The battery provided energy. Now, does the light bulb use energy? Does it use energy from the charges, or does the light bulb provide energy to the charges? Use energy or provide energy? Somebody said it. I heard somebody say it uses. Yep. So now here, this bulb has used 9 joules of energy per charge, or it has used 9 volts. Remember, a volt is a joule per coulomb, or a joule per charge. So we were at 9 volts of potential here, and then in the process of going through that filament, now we're at 0. This one bulb has used all of our electric potential. We're at 0 volts, 0 volts, 0 volts, 0 volts. There we are. Yeah. So now if I go through and I write down those values, here we said that was 0 volts, that was 9 volts, that was 9 volts, and that was 0 volts. So we have the electric potential kind of marked at those different spots around the circuit. One other way that people will go through and do this, well, maybe, here, I'll go back one step. So one way of looking at the loop rule is to say, if I start at one spot, comparing everything to where this black probe is, if this is 0 volts, I can add things up. And as I go around that path, one way of stating this loop rule is that when I go around this path, when I get back to that same point, that potential will again be 0. So that's one way of saying it. Another way of saying the loop rule is saying, hey, if I look at the difference in voltage across all of the different things that are in our circuit, and now really if the wires and the ammeters act like frictionless surfaces or electrically resistant. They're kind of just like empty tubes, right? Or not empty tubes, but they're kind of like just surfaces that just allow things to happen. So the things that exist in the circuit that actually do things are the battery and the light bulb. So if I'm going to look at the battery and the light bulb, I can say there's the voltage between, or the voltage across the battery, there's the voltage across the light bulb. And if I just compare those two, the voltage across the battery is plus 9 volts. So I can say here, this is plus 9 volts. And then when I go to the light bulb and I just check not across, I'm going to move both of these probes. So if I check just the potential only across this light bulb, we'll see that it is now a negative 9. This light bulb is using 9 volts of potential. So that's minus 9 volts. So I can go back up here and say that's minus 9 volts. So if I take the voltage across the battery and the voltage across the bulb, or the light bulb, I end up getting 0 volts. So that's another way of looking at the loop rule, saying I'm going to look at the change in potential across each element in that circuit. And if I add all of those differences up as I go around, I get a total of 0 because the battery provides it, the light bulb takes it away, we're back to 0. And this method for using the loop rule is helpful when we do other things later on. If we need to know the voltage or the electric potential across the bulb, then we can use the loop rule to find that out, and we can do some other calculations. It ends up being a pretty useful deal later on. So there's part 1 for a series circuit. Okay, a quick part 2, a series circuit with 2 bulbs, still looking at the loop rule. Our voltmeter still measures the electric potential or the voltage. Wherever we put the black is where 0 will be, and wherever we put the red, it'll compare that to the black. So if the black one here, we're now saying that's 0. So when I put the red probe there, it should read beep, there 0. So we've got that. Now with this battery, I didn't do any putzing, so this will just be whatever the battery normally is, 9 volts. So we're at 0 volts, and now this is like a plus 9 volts. Yeah. So if we go through and we look at the things that we've got, here we've got the voltage of the battery is plus 9 volts. Then if I go up and I move this probe to another spot, it's still 9 there, it's still 9 there. When I get over to the other side, it should end up being different because, like we've said, the light bulbs use energy, so these use voltage, they take energy away from the charges. If I go and I use this, the second way we can use a voltage probe, we mentioned this just at the end of the previous part of the video, if I put this probe here and this probe on the other side, well now this is 0, this is what I'm comparing it to, so if I put this on the other side of the bulb, it will tell us what electric potential or voltage this light bulb uses. There we get a negative 0.45, so that's minus 4.5 volts. So I can say that we're doing minus V, I'm going to say it's light bulb 1, and down here that's minus 4.5 volts. And there's only one element left in this circuit, so when I go over here, I can go through here and I can figure out or measure what this thing should be. But we can also go through and use a different way to predict what that should be. We could also go through and say, hey, if I use my loop rule, I can do minus the voltage of light bulb 2. And when I do this bit of math here, those things, when we put them all together, they should add up to 0. So I need something to put in here. So 9 volts from the battery, minus 4.5 volts from the first light bulb. Whatever we put in here has to get us back to 0. 9 minus 4.5, what must the voltage be for this light bulb to get us back to 0? What's the voltage use of this light bulb have to be? Yeah, it should be 4.5. Let's check and see. So if I go there and there, we get a negative 4.5, just like we were saying. And so that's minus 4.5 volts. Sorry, drawn with my thumb. As bad as my handwriting is, it gets worse with my thumb. So we have plus 9 volts from this thing, minus 4.5 here, minus 4.5 here, and we're back to 0. So we're going to do one thing just slightly different on our next set, still looking at a circuit very similar to this. Give me 1 second. Okay, so what we're going to do on this video, almost the exact same circuit setup, but we're going to change one thing. So on this bulb, I can go through and I can change a characteristic of the light bulb. So I'm going to put this one up at like 12, 13, 14 ohms for that one. And here I'll change this one. I'll change a characteristic of this bulb also. And there you go. Oftentimes when we were doing our stuff with circuits, we were saying, hey, assume all bulbs are identical. I've just made it so that these are different, and we see that they have different brightnesses. So this is a unique setting for what we've done. But rules are rules, and they work. Conservation of energy as a rule works, and that's kind of the foundation of our loop rule. So if I go here, if I can still go through and do that loop rule stuff, where I can say the electric potential that the battery provides minus the electric potential that light bulb 1 uses minus the electric potential that light bulb 2 uses should still end up getting us back to 0 volts. So we're saying the battery provides something, the light bulb uses something, this light bulb uses something, and we're back to 0. So we'll go through and we'll check things out and see what we can do. We didn't make any changes to the battery, so if that's 0, this top end is 9 volts. So down here, I can say I'm at plus 9 volts. Plus 9 volts. Bloop. Then we can go through and we can check this bulb. And then after that, we'll try to predict what this one was. So if you remember on the previous example, we had 2 identical bulbs, and if this was plus 9 with 2 identical bulbs, each of these was minus how much? Yeah, with 2 identical bulbs, each of these was minus 4.5. Now they're not identical, so probably not going to be 4.5. So we can go through and we can check and measure this one. There we go. So this one, the numbers could have been easier. This one is minus 6.63. So we can go down here and we can say minus 6.63 volts for that one. Now, before we go to measuring this one, let's go through and take a second to see if we can predict what it should be, right? So plus 9 volts minus 6.63 minus VL2 should equal 0. So you can pull out your calculator and say thank you to your computer overlords and ask that thing to calculate that for you. We can ask the calculator, say 9 minus 6.63 and see what it gets us. Well, if it were 9 minus 6, it would be 3. So you can try to do that in your head. You can try to punch that into your calculator, and this is a 6. That doesn't really look like a number. That still does not look like a number, but I might be able to convince somebody that I mean for that to be a 6. So that was 6.63. So if you've got your calculation there, now we'll go through and we'll see if we get the same thing when we measure this one. Hey,